In this video, I'd like to talk about the equations of lines, also known as linear equations. So here you can see I've written one example of what these look like, and another way to reference this sort of equation is that it is a two-variable linear equation. And with that, you can see clearly that there are two variables. We now have x and y. But it's also linear because x and y are both to the first power. Remember, if you don't see an exponent, it's like there's an invisible 1 there. And an example of nonlinear equations would be something like x squared, or the square root of x, or x times y, or x squared y to the third, something like this, where either x or y are multiplied or divided together, or you have square roots or squares, or something like that. But if you have none of these and you just have essentially x and y both to that first power, then we have a linear equation. So the question is, how do we interpret this kind of equation, or how do we deal with it? And the simple truth is that, like most of our one variable linear equations, we're always trying to find a specific value of x. But this time, there are actually an infinite amount of solutions. So essentially what that means is that if I choose a specific x value, then there is a specific y value that corresponds with that. And I can choose basically any x value, and with every x value there's going to be one unique y value that is associated with it. So what we can do with this equation is make a table and essentially look at, for given x values, what does y look like? And we're going to see if there's some sort of pattern that pops out. So let's make a little bit of space, and I'm going to make a table. Actually, let me just rewrite this down here. So y is 2x plus 1, and then we'll make a table now. So what I mean by that is we will choose specific x values and see what their y values will be. So we'll put x there and y there. So for instance, when x is 0, we would plug 0 in here. So we'd have 2 times 0 plus 1, and that's simply equal to 1, since we have 0 plus 1. Now I can plug in x equals 1. So again, I'm plugging in the same spot. So I have 2 times 1 plus 1, and so that's 2 plus 1, which is 3. And now if I plug in 2, I have 2 times 2 plus 1, which gives me 5. And you may start to see the pattern now. You might be able to guess that the next one's going to be 7. But we have 2 times 3 plus 1, so that's 6 plus 1, which it is 7. And so essentially every time we're increasing x by 1, the y value seems to be jumping up by 2. So plus 1 each time there, but on the y side, we're adding 2 every time we take a step in the positive direction. Though with these, you could also consider negative numbers. You don't have to solely restrict yourself to positive numbers. And if we plug in negative 1, then we'd have 2 times minus 1 plus 1, and that gives us minus 1. So notice, from 0, we subtract 1 to get this, and from 1, we subtract 2 to get this. So the pattern does still continue. It's just if you go backwards, you subtract by 2. And just as one final example, you can put in minus 2, and we have 2 times minus 2 plus 1, so that's minus 4 plus 1, which is minus 3. And so now we essentially have a whole bunch of coordinate points that we can graph. For instance, from this top one, we have 0, 1. Remember, x is always written before y. And then we have 1, 3, 2, 5, and 3, 7, as well as all the negatives, minus 1, and minus 2, minus 3. So with these coordinate points, we can now graph them, and hopefully we'll be able to connect them in some way that's meaningful. So let me draw a coordinate plane. So now that we have this coordinate plane, and let me rewrite the equation real quick, we're just going to start plotting these points here. So let's start with 0, 1. So 0 for the x value. So along the x-axis we go to 0, which is here, and then we just go up 1 for y. So that's 1 point. And then we have 1, 3, so 1 in the x, up 3 in the y, and we have 2, 5, and 3, comma 7. And we also have -1, -1. We have -2, -3, and so on. But what you can see is that there's a clear pattern here. These are all showing up essentially on the exact same line. So let's see if we can get a reasonably clean line to go through all of these. And with this line, you'll see that it's not perfect because I drew this by hand. But if you did draw this perfectly or with a computer, it would be an exact line, and these would line up perfectly. But from here, there are two things that we can take away. And they're two separate concepts. But notice that there's an idea called an intercept. And essentially, an intercept is when the line will cross one of these axes. So, for instance, in regards to the y-intercept, that's where does the line cross the y-axis. And notice that it crosses at that point 0, 1, or it has a y value of 1. And what you can notice from our equation is that we have this +1 on the outside. And it's not coincidence that that +1 also matched up with the y-intercept. And in fact, if I gave you a random equation like y equals 3x minus 2, you can immediately tell me the y-intercept is at this -2. So if we were graphing this equation, it would be at -2 for its y-intercept. Now, you may have also noticed that when we're looking at our pattern and our table here, that as x went up by 1, y always went up by 2. And notice that we had this 2 as a coefficient on x, and that again is not a coincidence. So these are related to each other. And this 2, this coefficient on x, is a concept that we call the slope. And basically what the slope is it's looking how much does our function rise divided by how much it goes left or right, which we call run. So you can see if I go from one point to the next that it went over 1 unit and went up 2 units. So we would say its slope would be the rise, how much it went up, divided by how much it went over. So our slope in this case would be 2 over 1, or 2. And that's true for all the points, because notice if you run 1 here, you have to rise 2 to get to the next point on the line. And that will be true for every part of this line. The slope is constant throughout the line. And noticing this other equation here, this 3x minus 2, this 3 would be our slope here. So instead of going up 2 over 1, we'll now be going up 3 over 1 for our rise over run. So as a preview of what's to come, if you were to graph the equation y equals 2/3 x plus 3, the number added on the outside, remember I said, was the y-intercept. And that essentially tells us where the line goes through the y-axis. And then this thing here, this 2/3, this coefficient on x, this is what we call the slope of the line. Remember, it's the rise over the run. How much does the function go up divided by how much it goes over. And in this case, we have 2 over 3. So every time it rises 2, it will go over 3 units to the right. So let's graph a quick sketch of this just so that we can see what's going on. So now that we have the coordinate plane, we can actually graph this line. And recall that we can start with this y-intercept. We know that it goes through the point essentially 0, 3, where 3 is the y value of that intercept, where it's going through this axis here, this y-axis. So that is this point right here, 0 for x and 3 for the y. So this is where it will cross this line. And then our slope tells us our next point, we can go up 2 and then over 3. So we'll count up 2 points and then over 3 points, so that's right there. And with an equation of a line, you really only need 2 points and then you can connect them. So let's connect these 2 points. So that essentially will be the graph of this line. Now, if I gave you an equation like this and you forgot the pattern of what the slope means and what the y-intercept means, you can always make a table. Start with x and y. When x is 3, then y is 2 plus 3, 5. And you can kind of keep going through that process. Choose when x is 0, y is 3. When x is -1 and so on. You can always make a table if you forget how to actually follow the patterns. But in future videos, we will cover this concept in much more detail.